Okay, this session is on correlation. This is a very common analysis procedure that that you should be familiar with. I'm trying to adjust this window so that you can see my face, but not everybody else's there. It's about as good as I can do. Uh, and yeah, analysis process that's quite common and that you should be familiar with. It's something we'll do in the class. And you'll do it in your regular life if you do data stuff. So back to the data analysis garden of forking paths, where we make a choice between comparing groups and looking for relationships. And a reminder that there's many other paths, many other forks. But this is just an overall framework for analysis of biological data that I think is helpful for folks in their first analysis class. So the big fork is are you comparing groups, like groups of 10 plants that receive different treatments, or are you looking for relationships, like we sampled ponds that have a different range of phosphorus emissions? And we've been spending our time on this comparing groups side kind of from the beginning, which is on purpose on my part, although I should maybe do a little bit more relationship stuff at the very beginning. But anyway, we've been focused on comparing groups. Now we're going to head down this path for the rest of the lectures into looking for relationships. Again, when you've each of these forks, a second fork, and we're on this side now, and we're going to focus on these two, and we're going to have one set of this lecture and then some coding to focus on correlation, and then we will have a separate lecture and some other work on regression. And then regression is the first step towards a whole bunch of other stuff. So a lot of stuff we do in data analysis is a form of regression. Like, model building, predictive models of any sort are oftentimes have underlying it a general linear model, which is basically a regression model. We won't pursue all of those unless you do the electives. I do have a empowerment elective on multiple regression that can get you started down that path. Which are like, oh, multiple predictors, multiple response variables, or whatever it might be, factorial designs, et cetera, et cetera. But for the class, for the main part of the class, we're just going to do correlation and simple linear regression. And today, we're going to focus on correlation. Okay, correlation is a form of analysis that tests for the relationships between two factors. In correlation, you are not assuming one causes the other, just that they are related. So here's LeBron James data again. This has been a great data set to use all semester. In this case, on the x-axis, I have offensive rebounds. On the y-axis, field goal attempts. And each of these points would be one of the games. And so this is a different way of looking at this data set. As one variable is changing, is something happening to the other variable? And as would be the case when you're doing a correlation analysis, this does not necessarily relate to this. This is not causing this. There's not a causal relationship between the two, although they are related. As you can see, more ORBs, more field goal attempts. And if you ever play pickup basketball, you understand why this would be true. Yep. Okay. So the relationship between two variables can have different strengths and directions. Here I have total rebounds and assists, and not offensive rebounds, total rebounds. And this is how you would set up a correlation analysis. So you have these two columns of data. See right here, see my cursor, total rebounds and assists. And in this case, as the number of LeBron James total rebounds increases, nothing happens to the number of assists, seemingly. This looks like just a smear of data, nothing going on here. Where you see a relationship, normally what's going to happen is as one increases, the other increases, or as one increases, the other decreases. In this case, we've got no relationship. So your correlations can have different shapes and different signs. So in this case, as x increases, y also increases. This would be a positive correlation. Here is one where as x increases, y decreases. This is a negative correlation. As one increases, the other goes down. You can also have no correlation. In this case, as x increases, y doesn't do anything. And in this case, as x increases, y doesn't do anything. There's nothing predictable about how y is going to respond to x here. This is just flat. This is kind of, I don't know what you call that, standing tall. There's no correlation between those two. You use correlation analysis if you're not making assumptions about one factor driving the other. You just want to know if one is related to the other. When we're going to make a prediction or we're going to assume causation, then we're going to use regression analysis, which is coming up in the next set of lectures. Okay, here we have a relationship where as x increases, y is increasing. This is a positive, seemingly a positive correlation. But other than just visually looking at this, we can also assess the strength of the relationship between these two variables statistically. So in this case, we will calculate two statistics of interest: A, the correlation coefficient, and B, the p-value. As is always the case, the analyst, you, or any of us, anyone who's working with data, should always think about your data set from the perspective of doves. Distribution, outliers, variance, effects, sample size. This is also true for any kind of relationship. So sample size could affect the number of points on here, could affect the relationships if they're bifurcated into into two sort of constellations or patches. If you had a really extreme outlier, if we had like a point up here, you go, what now? How big is the sample size? If you've got 3 versus 20 versus 50, all of these things, all of these things still apply. Okay, here, here we see another undead statistician, Nosferatu Pearson, in 1912, who came up with the Pearson correlation coefficient. This spectral character came up with the idea of this thing, which is a way to analyze the relationship between two variables. We call the Pearson correlation coefficient R. R is something we use all the time in statistics. This is the formula for this, and you'll recall, probably not, but earlier in the semester, I talked a bit about sum of squares, mean value, subtract each value from that, then you sum that. So now we've got x and y. Reminder, the variance equation, which we didn't really spend too much time on, but I did show you in class. You don't have to learn this. Just because of the way I teach the class, I've been through over and over again. I'm not going to make you like calculate this. It's not that hard to calculate though. It's like x and y. There's only two, and then you just like, what's the mean? Then subtract each value, then sum that, then multiply those. In any case, this is the structure of the correlation coefficient if you ever want to calculate it yourself. Okay, the correlation coefficient, the Pearson coefficient, measures the strength and direction of the relationship. It is a decimal, and it will lie between -1 and 1. Closer to 1 is stronger, the absolute value. So if it goes -1 or +1, in either case, the relationship is strong. We will also be able to test the statistical significance of this relationship and generate a p-value where the null hypothesis would be no relationship. And you would attempt to reject that null hypothesis, and you would set the critical value as p less than or equal to 0.05. All of the words I've said about p-values apply here. So it's 95 times out of 100, and all this false positive and crying wolf, and the caveats too, like, well, what if it's 0.059? What if it's 0.07? What if it's 0.0, whatever, 44? Is there really a difference then, or whatever? All of the words I said about statistical versus biological significance applies to p-values in the case of a correlation coefficient as well. Okay. So in R, we have a procedure called core.test that will generate the statistic of interest. There's probably, as always, many different ways to conduct a correlation analysis. But good news, the base package of R has core.test. And it will generate this bit of output in the console of RStudio, where it will say the Pearson's product moment correlation. That's the Pearson. We saw that person before. Ghostly apparition statistician named Pearson. And you'll get a p-value here. See that? This is points and assists. In this case, the p-value is 0.5. You also get this, and it's kind of weirdly labeled. It just says COR, core. That's the correlation coefficient. You really want to have both of these to assess your statistical relationship. Is it statistically significant? And then how strong is the relationship? And then what direction is the relationship? So closer to 1, whether it's +1 or -1, is stronger. And this has a critical value of p equals 0.05. In this case, we have 0.5, and therefore we would or we cannot reject the null. And we would say there is no relationship between points and assists here. So you can look at this. And also, if you look at this and doves this thing, you go, there's nothing going on. In other words, as the number of points increases for LeBron James from 2015 to 2016, each one of these points is a game. That has nothing to do with the number of assists. You don't get more assists with fewer points or more assists with more points. It's just nothing happening. Proof is right here, 0.5, and a correlation coefficient, which is negative, but basically no different than 0. Nothing's really happening. So slightly negative relationship here. Yep. And again, we're not saying that one is causing the other. The only question here is, are they related in any way, shape, or form? In this case, ORB, offensive rebounds, and field goal attempts, there is a positive relationship. The correlation coefficient, R, is 0.25, and the p-value is 0.0257. You'd say there is there's a statistically significant relationship between offensive rebounds and field goal attempts. This is a relatively weak relationship, however. 0.25 is not close to 1. Okay. One idea in passing, there is a thing called the Spearman rank correlation. This can be used for non-normally distributed data. It's a correlation based on ranks. As I've taught you before for ANOVA and stuff, there is like a test the normality and then go down one path, down the other path. However, the Spearman rank correlation, and this has happened maybe in the last 15 years because I learned this a long time ago and I use it in my studies. There's a bit of controversy around it, whether we should be using rank correlation or not. And so I don't know if some math people have words about this. So since there's enough controversy, I'm not even going to teach it. Just saying it right here to let you know, I would imagine this person is also 700 years old. Spearman, we should look up that person. Okay, the second idea is a correlation matrix. Okay, and I'll show you how to make one of these in just a minute when we switch over to R. This is a useful tool. And so, and I'll show you how to do one like in R. In some biological studies, not all, but many, you can have a lot of different variables that you're working with. Then they may have a relationship with one another. And sometimes it's good to have a snapshot of all of those at once. And that's what this is. This is a correlation matrix. You don't know what these are, but these are all a bunch of different values that had been measured on some plots. Aspect, elevation, slope, pH of the soil, phosphorus in the soil, calcium in the soil, cation exchange capacity. This is actually a measure of light. And here are all those values again this way, and everywhere they cross is their correlation. So aspect is 1 with aspect, that is completely positive relationship because it's the same numbers, okay? 24, 24, 26, whatever. And then this would be slope's relationship with aspect, pH's relationship. phosphorus with aspect, and so forth. So if you look at this thing all at once, you can see the bold is a statistically significant relationship. So you go, okay, I can just quickly scan this and see if there's anything happening. Uh, the reason to make one of these, I have to keep an eye on the time, 16 minutes. Okay. The reason to make one of these, if you're going to be a biologist and work with data sets, is sometimes there'll be stuff in your data that you're not expecting that might indicate a problem or might indicate like a really cool new thing that you weren't thinking about before. Many different researchers start their research heading down one path and they're like, get halfway into their stuff and they're like, what now? This is find something completely different. Their main idea or hypothesis is rejected and they've got some new thing that's happening that's even more exciting. Uh, that's the like excitement of discovery. This is a way sometimes, and again, you probably are zoning out here, but this is a way, if you can snapshot your data like this, sometimes you can catch something and you're like, what is happening there? Oh, this is a really strong relationship between base saturation. Or like, here's light is very negatively related to aspect or whatever. So you go, oh, I'm gonna check that out and follow up. Yeah. Okay, so I'm going to show you a couple of examples. There's no point for me to show you this, just to say that two of the examples come from the book, which is an optional book. Now we'll move over to our first. You should set up your YouTube channel for proper coding music. I'm not going to do it now because I think if it's playing behind my voice on a recording, it would be stupid. Bad choice. I can stop there. Anybody have a question? Okay. And I'm going to, by the way, in Isidore, I've got assignments here. Coding Club correlation. This was all set up to run like in class today before this thing happened yesterday. So I was going to do all this. But what I'll do is, as this thing ends now, I'll just go. It takes a little bit for the video to finish processing, but as soon as it finishes processing, I'll add it to this assignment. And so then you can just watch the video if you're not here. Those of you who are not here, you can watch it. Or you can watch it if you are here. There's a couple of parts to this. Part one is describe a situation with two variables in which you guess a relationship might generate the following Pearson correlation coefficient. So you need to imagine like what would be two things that are the two variables that are related in a positive and strongly positive way. What are two variables that are not related or have a very weak, extremely weak, or just no relationship? Once you get this far down, what would be two variables that are only negative related? You just think of them, okay? And then answer this question. And then the rest of this is coding stuff, which we'll do right now. Okay, moving over to our studio. Okay, correlation coding in R. This is, I got a few things for our agenda here. A correlation example using stream invertebrates from Whitlock and Schlueter. Excuse me, 16.4. A correlation example using wolf data from Whitlock and Schlueter. That's that book. That's an optional book in the class. Also, example 16.2. I will show you how to make a correlation using Lebron James data, which you already have. Also, how to make a correlation matrix, and then this really wild way to visualize your data using panel.smooth. Okay, so we're going to start. Go ahead and open up RStudio. I'll give you a second to do that. Some people are in the room, so I actually need to wait. If it was only a video, I could just say pause the video. Get RStudio open and go ahead and activate your libraries, Grid Extra and ggplot. We will use both of these today. And then we're going to start out by using some stream invert data. Let me just switch this. This is too hard for you to type, But good news, I went ahead and wrote the CSV uh, and posted it on that Isidore um, assignment, which is open now already. Coding Club correlation opened at 9 a.m. You can go onto this and download the data, the wolf data. We're also going to use the stream invertebrate data, so go ahead and grab those data sets. I will, I can also email it right now. Probably don't need me to do this, but let's see. Nope, I'll see. Oh no, so this is on mine here. Okay, let me write it. Inventory.csv. Okay. And then the other one's going to be this wolf data set. I need to write that one also. Potentially, yeah. I'll read that in, then I'll write it, and then I'll post it for you here. So if you can't get it, I don't know why you couldn't, but it's probably a waste of our time for me to do this right now. But here it comes anyway. We'll use both of these. Okay, so um, yeah. So first, we're gonna read in the wolf. We're gonna let's see. No, we're gonna work with the stream invert data first. So go ahead and pull that in. You'll use your however you do it, files, whatever. And as always, I like to once the data come in, I like to do this to see it down here in the console, or to do this just to be able to see it up here. You want to make sure that RStudio actually has the data before you're trying to write code and telling it to do something. These are easy ways to do that. You don't need to write this code. This was just me creating a CSV file. I pulled the CSV file off of the Whitlock and Schlueter website. All right, so now let's make a graph. In this case, we're going to do the dataset name, stream invert, with a capital I, comma, AES, aesthetic element, open parentheses, Y equals log density. And you would have to go look at the head again to find out what your columns are. If you're going to do a correlation analysis, it's just generally speaking, you're going to have data in columns like this. You're going to go log density versus log mass like that. And then the rest of this is kind of details. So I use Firebrick, but if you just like close this and go like this, you can get like the most basic plot. If that makes sense. The rest of this is just customizing the graph. So uh, type the code. I'll give you a second to do that. There's gotta be a way to just show my face, but I don't know how to do it though. Okay, uh, so once you've got this graph created, and again, you can make a simple version of it. This is a more complicated version of it. Uh, the next thing is doves, right? It's like take a look at the data set and um, see what you got here. A sample size. We don't have any outliers. It doesn't look weird. This is made for use in a class, basically. So um, it's kind of a perfect data set for this kind of analysis. Oh, that's just better. You can at least kind of see me there. Okay, that's good. Um, yeah. And so what we have here is body mass and population density, and this is from stream invertebrates. Those are little critters that live in the stream. And the basic relationship here is population density and body mass are related. This seems like indicating a competition sort of thing. High density is low biomass. Low density is high biomass. So it looks like you've got a correlation here that it would be and just like quickly snapshot of it would be a relatively strong and significant negative correlation. And then you can write up the core test this way. There's other ways to do it too. You can use a tilde and comma data equals. Um, in the past, I felt like students most clearly understood this: data set name, column name, comma, data set name, column name, close bracket, with a dollar sign here as the connector, and then a comma there. And this is core.test. This is the correlation test. And then you just click on there and run it. And down below, it will generate your, yeah, this is up there already. So it will generate your outcome. So this at the bottom is in your console. You will have the Pearson product moment correlation. Tells you what the data are here, and then you've got the p-value, which is negative E16. That's like a lot of zeros, okay. Way below 0.05, so very strong. And your correlation coefficient is negative 0.76, so that's very strong negative correlation. So you've got a lot of power here too. Okay, um, that's how the correlation coefficient and correlation analysis works. Pause here in case someone wants to pop in. Okay, and that's it. Analysis complete. I do. You don't need to type this code, but I do want to say I want to walk through this real quick because it was in the book and I thought it was an interesting thing. So this is not expected in the assignment, and you don't need to do this. You can if you want, and you can go back to the video and get it if you want. I'll go through it a little bit quickly. Um, this is just on the importance of scale. This is like a biology comment. So this is a really strong negative correlation. But now we're going to take a subset and we're going to look at between 0 and 2 only. So this is a way to create a new subset, which I'm going to name that reduced. And again, just flow with me here. You don't have to do this for the purpose of the class, but I think it's a cool and interesting and important point for you as a potential biologist. So I'm just going to run this code to make a subset, and then this is the same basically as before, but instead of using this is just copy and paste. But I use the word reduced here because reduced is the name of this new data set I created, which is a subset, and it's subsetting the data only between 0 and 2. If we run that, we get this, which is just a of data. And the core test. Oops, wait a minute. Yeah, this should be say. Oops, I messed this up. Reduced. Is now a positive, or it's above the threshold, and so there is a relationship here. but it's weak, and it would be statistically, if you use a 0.05 cutoff, it would be not significant. So you still have a negative correlation coefficient, but the p-value is 0.07 now. Remember we had like 10 zeros or whatever in the other one? The whole point of this is simply, and maybe I shouldn't have even done this, but I think it's useful. It goes back to like the first point I made in class, or one of the first points I made in class, which is, and I'm just going to grid arrange these. Did I turn grid arrange on? I think I did. Which is you have to understand the biology of the system you're working with. So if you're interested in the relationship between body mass and population density, and you're like, oh, I'm going to conduct this research project. What happened to it? There we go. I'm going to conduct this research project, and uh, the the part of the population you're working with was only here, you would say, well, there is no relationship. But if you collected samples across the full range, this is called the full range, then you have a really strong negative relationship. So this is just a quick aside on the importance of scale in correlation analysis. So you have to make sure that the question you're asking is biologically reasonable and will capture the variation that exists in your population. Okay, end of. Okay, now we're going to do another correlation analysis, this time using wolf data, also from Whitlock and Schlueter, which I just emailed you briefly a few minutes ago. And I also in the Isidore site. I'm going to read it in from the internet like this. I already wrote that for you as well. And we'll follow the same process. Here is the graph. Again, the data set is named Wolf. Aesthetic elements, X, and you would want to like take a look at it some way, shape, or form like this. I just asked what it was and put it in the console like that. Or you can do view, you can do head. So we've got two variables, inbreeding coefficient. This is among wolves, and this is the number of pups. And the relationship here is that as your inbreeding coefficient increases, the number of pups seems to go down. This looks like a negative relationship. Again, if we could just do a quick doves of this, and you could, again, if you wanted to have a more simple plot, you could just do it like this. I put a little bit more pizzazz here. Breeding limitation in wolves. As the inbreeding coefficient increases, the number of pups in the litter goes down. This is a real data set. I think both of these are real data sets actually from ecological studies or biological studies. Doves, you go, okay, sample size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, whatever. This is like a good number. We've got no outliers. We don't have any thresholds. I should talk about this probably maybe in the regression analysis part. I'll try to circle back to this point about thresholds. Sometimes when you have relationships between variables, there can be like a breakpoint or a threshold. Don't see that here. Looks like a smooth negative relationship with a big enough sample size to run a test. Yeah, looks like a strong negative correlation. So then we can run the core test like this. Core.test wolf is the dataset name. We have two variables, inbreeding coefficient and a number of pups, and method equals Pearson. Did I have that in the one above? I forgot. Yeah, the default is method equals Pearson, but you could also name it this way. I did that because if you did want to run the Spearman correlation coefficient, you would put method equals Spearman there. But anyway, the default is the Pearson correlation. You can also sort of demand it, use Pearson this way. If you do that, then you'll get the Pearson product moment correlation as before, where you've got the p-value 0.00163, and your correlation coefficient is negative 0.607, so negative 0.61. This would be a strong negative correlation, and it would be statistically significant. So you could say the, there's a correlation between inbreeding coefficient and number of pups. It's a negative correlation. You can't really say one's causing the other. Other things happening, but this is definitely intriguing and something that you could potentially report as part of your paper or whatever. There could be some kind of issue with loss of vigor in the population based on inbreeding. If you've got small populations, there's a thing called an extinction vortex a population can get into, where there's a small number and their inbreeding causes, causes a lack of fecundity, the reproductive rate slows down, and there's fewer. There's even fewer, and there's even fewer, and then more inbreeding, and even fewer, and more inbreeding, even fewer. So anyway, so this is core test. Yeah. Last one. I don't know if I'm going too fast or too slow here. Is LeBron James data, so I'll give you a second to get that in. Libraries, we already have those turned on, but we can leave that here. So you've got the LeBron James data somewhere. We've been using it all semester. I'll give you a second to get that in. Okay. So once you have the data in, we can draw a graph. I did spend some time fancying this thing up. Again, you can just do this. Give me a second to do the coding. I'll play some drums here while you're working. I need to be able to play softly and slowly though, just to help. Some good coding drumming. Is helpful. You can, if you want to customize, this is what I did. It's a little bit extreme. I took out the theme classic, just takes out the, just FYI, and I do have, as I mentioned before, I do have that elective customization, figure customization. But an easy way, if you just like don't like the, if you don't like the this kind of net in the back, you can take that out using very simple code, theme classic, open parentheses, close parentheses, plus. And then I threw this border around it. If you take out the border, again, this is just like kind of fiddling with code, but it does this. But the theme classic will eliminate the rest of it. But I kind of like to have a box around it, so that's what the theme dot border is. You don't need to do all this, but you can. Okay, and here's the core test. Core.test points ORB method equals Pearson, and you can click on that or run it like this. Core test, and that will give you a p-value of 0.0254. So this is what we're seeing here. And the correlation coefficient is positive 0.25. So this is a relatively weak but positive relationship that's statistically significant. It's also logical. It's helpful when it makes sense. ORB is like you just got the ball and you're probably close to the rim, so and you're on offense. So there's a reason why you might get more points. But it doesn't. These are also it's not causal. You could also throw the ball to someone else or just dribble it off your knee. So it's not a causal relationship, but it is a significant positive relationship. Um, yeah, I don't know if you're with me or not. Hopefully that made some sense. But I'm going to show you a really simple code. So we can test the hypothesis of no relationship and assess the strength of the relationship among all of our numerical variables in this data set. So if you're working with a big data set, let's see what time it is, 10:15, good. So we're working with a big data set, like you might be in a study where you're like, oh, I've counted the number of grasshoppers in a prairie, and now we've also measured the soil, the number of flowering plants, the number of grasses. We've measured all these things. We've got all these variables, and they're all numeric, and they're all quantitative assessments of the environment. You might be like, I really kind of want to know which of these relationships, which of these variables are related. And if you're, even if you were a consultant for LeBron James Inc., you would be like, you might want to know that too. You're just like, we've got all of this data from 2015, 2016. Are there relationships here? Are there some things that are happening during the game where one is affecting the other that we're not thinking of? Like this could be a process of discovery for you. Um, and so if you want to make a really simple code that doesn't even use ggplot, and you're just like, I want to, as fast as possible with as many few clicks as possible, uh, just like quickly look at two relationships or two variables. You can do it like this. This is the simplest, kind of the simplest possible code to draw a plot. It doesn't even use ggplot. And then of course you could just change these up. You can go, okay, points and ORB. Let's look at that. Okay, what about DRB? Okay, let's look at that. You can just kind of mess around here. FTA, free throw attempts. Oh, well, this makes sense. This starts to become more obvious. Is it steals STL? I don't remember. You'd have to go back and look. Yeah. So you can see I'm just exploring. And if you've got a big data set, you might explore this way using the very simple code. And I'm just hitting run each time. Just plot. It's just the code is simply, and this is base code, not even ggplot. Plot, open bracket, LBJ $ points, tilde, LBJ $ whatever else. And you can change this one too. Oh, I want to try assist and steal. This is a way of exploratory data analysis for you to make discoveries. And if you find one you're like, oh, I really think this is interesting, this one does not look interesting, steals and assists, but we could just run the analysis, see FTL and assist. The simplest code is like this, core.test, and then the exact same here, and you can look p-value 0.5. Nothing there. Yeah, so I already did this part. So it's like scrolling through and checking out a bunch of different variables. However, here we have a large and complex data set. And doing this can take a lot of time, and it's kind of annoying, and there's got to be a better way. And so let's take a quick look at the data set here. I just clicked View LBJ. Just make sure you're caught up. I gotta slow down here. Okay, so if you just go a little slower. Okay, so if you look at the data set, you can go, okay, I'm interested, and this could be the case in your thesis research too. You're like, I've got all of these variables, points, PF, personal fouls, I guess that is, plus minus, turnovers, blocks, steals, rebounds, offensive rebounds, free throw percentage, free throw attempts, three pointers, on and on and on. Okay, you got all these variables. Some of them are not numeric though, like opponent and WL. This is not numeric. You've got a whole bunch of numeric variables, and you've got some that are not numeric. And you could have some that you're like, this doesn't really make sense to analyze. as well that you want to throw out. This is a time when you might say, what I want to do is create a correlation matrix that shows me the relationships between all these variables. But I can't do that if I've got numerical variables. So then I'm going to need a subset first. So the idea is like, I've got this data set I'm interested in analyzing. However, I don't want to, like, names don't make sense. TM, it's not even going to work. You can't do a correlation of TM Cleveland because he's only on Cleveland the whole time. Like, this doesn't make sense for an analysis. So we'll want to we want to take a look at all the data to see if any are correlated. Problem: there are many variables, and some have numbers and some have letters. Some are not quantitative. So first, we're going to create a subset of numerical variables of interest. There are many ways to subset. We've been through this a number of times in class. This is one way to do it, and I won't go through these other ways, but we'll just do this for now. The way to do this is LBJ underscore NUM. This is, you name it whatever you want. This is what I'm going to name it. You want to have the same name as me though below, because I'm going to do some stuff with this down here. I'll skip some of this stuff, but here you're going to use that data set LBJ underscore NUM equals LBJ is the data set. This has to be a hard bracket. C is for concatenate, open parentheses. Then here we're going to just put in I just forgot what this is, quotation marks, any of the variables you're interested in. We won't pick them all, but you're going to pick a subset, and then make sure there's a comma between, then close with this close parentheses and close with this bracket. You can pick others, and you don't have to put all of these in here. Again, you would kind of go back and forth, and you'd be like, okay, what do I really care about in this? Well, I don't remember what I picked, but field goals, free throws, offensive rebounds, defensive rebounds, assists, three-pointer, three-point makes. I guess that's what three-point M is. Yeah, three-point makes, STL, steals, and blocks. Note that this, whatever the data set you might, the other one I had before was like phosphorus and calcium and whatever, potassium and soil nitrogen and light. I had a big data set of all these environmental variables or whatever the variables in your data set you might be, but you might also have things that are like, as we have in this case, some variables that don't make sense. Also, just to say, subsetting is a key skill for you to have, and this is just another go through that. You might subset in many different ways. All right, type the code and run the code, and you'll know that it worked when you just can type this down here and run it. Or you could also, of course, do view LBJ underscore NUM. If you click that, nothing happens, and you're like, oops, it didn't work. But if you click it and it comes up here, now you say, okay, now I've got a different data set. Now it's just these. I've gotten rid of all this other stuff. I don't have WLs, DIF. This is negative values here. I don't know if that would even work. OPP. You probably could use DIF, but anyway, you can use OPP or WL there, and maybe some of the other stuff you don't want, whatever. There is also ways to subsetting by deleting columns. You're just like, the ones, I want everything except these, but for the purposes of what we're doing now, let's just leave this alone. So make sure you got that subset created. I don't even know if that comes through the sound. Anyway, there are other ways. This would be, and we won't do it for now, but I'll leave this when I share my code. Or if you want to just type it up real quick, you could. You can also, this has got LBJ core. I just had a different name. Here's a data set. Leave a blank here, then comma, then concatenate, and then this is the column numbers. So you'd have to go back and go, okay, 1, 2, 3, 4, 5, 6, 7. All right, MP, and it's 25 total. So it gives me everything else. I just cut out the first set. That's what this would do. And again, you don't have to do this. This is like a little bit advanced, but if you're going to be like, oh, I'm going to do data analysis, then you want to learn how to subset really well. So this is like, now I've cut that first bit out. This stuff's all gone. And I just got these left. This is very simple code to do that. Okay, very simple code. Here's another way to subset. You can list specific columns. Like I only want 7, 10, and 12. So I'll leave that one alone. All right. Now, back to the last couple things to do in this session. Back to the matter at hand. So here we have, I'm going to show you how to generate a correlation matrix. And this is using the LBJ-NUM subset, which we made before, this one. Again, if you run the correlation matrix and you haven't done the subset, then you're going to have stuff in there that doesn't make sense. It might just break. It might just be like, no, man, no, I can't, dude, I can't correlate. I can't run a correlation with Chicago, Memphis, Miami, okay, versus 12, 4, and 13. It's not going to be a thing. So you have to subset just to get numbers. Can only run a correlation with numbers. But if you do that, you can get, and it shows up, it appears here below in your console. Here's a correlation matrix. Now, there are packages. I had a student in class years ago who went and found a special correlation matrix package, which will generate this in a more aesthetically pleasing way. Of course, you could easily just copy and paste out of here. So like, you know what? I want a correlation matrix. But I'm going to copy and paste and put this in an Excel sheet or put it in a Word document or something to, to share with my PI or whatever. But the way you interpret this is what I showed you before. And this has got like, there's a diagonal of ones through the middle of it. If you can follow me here. The diagonal of 1 to the center of it, that's because defensive rebounds has a perfect correlation with defensive rebounds. Okay. In the columns, it's the same number. They're identical. So there's a diagonal of perfect correlations and then perfect positive correlations. And then off of that diagonal, everything else would be like, this is points and field goals. So 89.89. That's a very strong positive correlation. Well, this makes sense because, and again, in your study, hopefully you know the biology of the system, but I know the biology kind of this system, and I know that field goals and points better be correlated positively. If it's not, there's a problem. You can't shoot, literally. Offensive rebounds has a positive correlation. Defensive rebounds, no relationship at all, or barely. 0.1. Now we don't have the statistical significance in this yet, and there's ways to do that. Again, a package you can get that will probably color these for you and generate a graph or whatever. But if you're just like, I'm just going to quickly scan my data, this is an easy way to do it. I can find out what's the correlation between points and all of these things. And steals is 0.009. There's nothing there. Blocks is 0.03. There's nothing here. 3-pointers, 0.5 is a strong positive correlation, which it should be. And then what you would do is be like, okay, I'm going to follow this up now. Like, this looks like something interesting right here. Let me go make another graph, and then you can go write the graph, and you can make it, very pretty, and you can do, clean it up really nicely, like some of this code here. And you can make it, fire brick or something. Honeydew 12. Yeah. There you go. This is a correlation matrix. Basically, you don't get the p-value that you do with the core test, but you do get the correlation coefficient. Just to make totally sure everybody understands what's happening here, is this is the number you're getting in the correlation matrix. Did you follow that? So you have this core test. The core test generates a p-value and the correlation coefficient. If you just want a matrix that's all these values of just the correlation coefficient, you can do it this way. And the correlation coefficient tells you the strength and direction of the relationship. Okay, we good? Can't see your faces, so it's hard. In class, I can tell usually. It's just like, this is like, person's been asleep. They're wiping the drool. Like, what now? Is this guy still here? I can't tell anything now. No faces. That's okay. We'll assume that you got it. So, correlation matrix. Now, last thing in this section is something I did not discover this. Some student in class discovered this and showed it to me. You can visualize. I'm going to sweep this. So go ahead and sweep your chart space, and you need to make it big because it won't fit. This is in base code. There's a thing called pairs. So we're going to do pairs, the LBJ, open parentheses, LBJ NUM, which is the data set we created, the subset of data set, comma, panel equals panel dot smooth. This is the code. I've only scratched the surface with this because some student in class like years ago was like, hey, Dr. McEwen, did you know you can do this? Panel dot smooth. I don't know where they found it. It was Stack Overflow or something. I was like, no, I did not know you do that. So it gets a little scrunched in here. And I'm sure we could explore this in different ways, but when you run that code, this is a good thing to do is zoom it like this. This is basically a visual correlation matrix, which is a really mind-blowing chart. I feel like there should be applause when I do this because it's so awesome. So what we have here is a diagonal, as I showed you in the correlation matrix, but it's points, field goals, free throws, ORB, defensive rebounds, assists, three-pointers, steals, blocks. And then each of these, like right here, can you see my cursor? I need to make it bigger in orange or whatever. But this is a visualization, a graph of the relationship between field goals and points. And this would be the relationship between free throws and points, and free throws and field goals. So you can quickly look at this and go, okay, what's going on here? You can just let your eyes kind of roll over this. We already saw this graph before. Offensive rebounds on the X, points on Y. I made that earlier. See this? And it's throwing this little weird squiggly line. I forgot what that's called. I don't like those lines necessarily. I wouldn't use those lines in my research. But for the purposes of a graph this size, it does give you a sense of like, it's a low S curve, actually, is what it's called. Anyway, I don't like those, but it does give you a sense of like what's happening with the data set. Like here, 3-pointers made and points. This is a pretty strong positive relationship. And again, you can go back and redraw that graph and make it nice after this. But if you have a huge data set, you're like, I don't know what's going on with my data set, and it's numeric. This is a tiny bit of code to run where you go, now I can visualize everything that happened. I can see everything. If you spend like, I don't want to export it, but if you spend like, oh, I'm going to spend 10 minutes looking at this, you might have 5 new discoveries that weren't part of your original thesis project that you're like, oh, this is pretty interesting. Like there's some correlations in here that you could then subsequently explore. You wouldn't publish this necessarily, but you would use this as a way to explore all these correlations and then follow up and go, okay, we've got this really strong relationship between, this is something we'll explore in the regression lecture coming up. And actually 3-pointers and points, there is a actual causal relationship between these. So this needs to be a regression approach, which we're going to investigate later. But ORB, this is like a little bit of a positive relationship here or whatever. Then you create a nice graph, ggplot graph, with things that you've customized and statistics that you've generated using a Pearson correlation analysis. That's a formal analysis, and so you can present the p-value and the correlation coefficient in your thesis. So that is the conclusion of what I had planned for today. That is correlation analysis. So I'm going to stop recording now, and then we'll see if people have questions.